Hello everyone, my name is LiangYuan. My project name is Image Registration Study and an Implementation in Image Stitching. First, here is the outline of the presentation. The first is introduction and approaches, and third, we will evaluate the results, and finally, we will give the conclusion. Image registration is the process of transforming different sets of data into one coordinate system. It is necessary in order to be able to compare or integrate the data obtained from several different measurements. It can be used in several areas such as medical imaging, military target recognition, satellite image analyzing, and image stitching. In this project, we will focus on the panorama image stitching, which have previously have some complex and professional algorithms, but it is not suitable for normal users and implemented in camera applications such as iPhone. There are basically three steps in image stitching. The first is calibration or create motion models, which can also be separated into several areas such as 2D motion, 3D transformation, and in this project we will mainly focus on the cylindrical coordinate system. And the second step is registration, which can be divided into two parts. The first is pixel-based and the second is feature-based. In this project, we will mainly focus on the feature-based registration because it is less complex and its time consuming is much less than the pixel-based registration. And the third step is blending. In this project, we will mainly focus on the simple linear blending. Other algorithms such as Laplacian pyramid blending also can generate satisfying results. Here is the flowchart of our program. And there are basically 5 modules. The first is image on distortion and cylindrical coordination reprojection. It is belong to the calibration step. And the second module is feature extraction. And the third module is pairwise translation estimation. These two modules belong to the registration step. And the pairwise translation estimation also can be divided into the loss matching and ransack iteration. And next we enter into the stitching and blending module, which obviously belong to the third blending step. And at last we add another optimization module called affine drift removal and result cropping. Approaches. First, we need to do image on distortion. As is known that all images taken from a camera all have a lens distortion on their edges. So we need to cancel these effects. We use these 3 equations to do the calculation. The F represents the focal length of the camera, and K1 and K2 represent the distortion parameters. X apostrophe and Y apostrophe are the original raw input image pixel coordinate, and the result is XY pixel coordinate. Another thing we need to consider is the bilinear interpolation, because the XY pixel coordinate may sometimes not be integer, so we need to translate this non-integer pair into 4 integer pairs. Next, we enter into the cylindrical coordinate reprojection. Here we have to do an assumption that all images are taken with a level camera and with a known tilt angle. This assumption seems like very narrow. However, it is suitable for panorama image stitching because we finally will generate a rectangular image. So here are the equations to calculate. Again, the F represents the focal length, and X apostrophe and Y apostrophe are the results given here. Now we enter into the SIFT feature extraction. The SIFT is short for scale invariant feature transformation, and it has mainly two parts. The first is descriptor vector. It has 128 length, and the second part is location vector, which has 4 parameters: the subpixel row locations, column locations, scale, and orientation. Here is an example of the SIFT feature. We notice that the descriptor vector has normalized values. And then we enter into the pairwise translation estimation. Here, the pairwise means that we do this estimation in a pipelining way, that we only compare the first image and the second image, and the second image with the third image, and the third image with the fourth image, so on and so forth, because we assume that the user will take the images in order, and so the images input are in the sequence. So we don't have to compare the first image with the third or the fourth image. And how do we do the estimation? There are two steps. The first is Low's method, which is introduced by David Low in 2003. And in Low's method, the feature Fi of image A and Fj is the SIFT feature of B. And its descriptor vector has the smallest Euclidean distance, the smallest from the descriptor vector of Fi. And Fk is the SIFT feature of B, and its descriptor vector has the second Euclidean distance, the second smallest from the descriptor vector of Fi. We need to ensure that d smallest over d second smallest is equal to or smaller than the distance ratio, and then we will choose this matching pair Fi, Fj, and enter into the ransack iteration. The purpose is to make sure the purpose is that the raw input data from the previous Low's method cannot directly be used because there are still outliers or false positives. So we'll do the ransack iteration. However, we are not interested in the residues. Instead, we look into the iteration times and the tolerance. Here, we assume that the motion estimate p equals to 0.5 and the likelihood p equals to 0.99, and the iteration times s will be given by this equation. And here we assume that since we only compare the 2D motions, so the k will be equal to 1 and then s equals to 7. And we now look at these equations. We have to make sure that this part is smaller than the tolerance. We here assume the tolerance equals to 5, and the t apostrophe represent the estimated translation, and x and x apostrophe are the feature coordinations of the first and the second image. We now enter into the stitching and blending step. Also, here we do the stitching in a pipelining way. That means we stitch the picture, the image 1 and the image 2 into the temp image, and stitch the temp image with the third image, and so on and so forth. But before that, we have another step that is called the global registration. Since that we already have the unified cylindrical coordinate system for the images. However, we do not have the unified coordinate system for features, so we need the global registration. First, let T delta R delta C represent the translation from image B to image A, and RACA will then be equals to RBCB plus T. Then we will need the new row and column indices for each pixel. Here it is calculated by RC equals to RACA plus the shift, and the shift is calculated by this equation. Then TI and SI represent the translation and global shift in the ith stitching, and the pairwise translation is given by TIP. Then Ti plus 1 will be equal to this equation. Then we enter into the affine drift removal step. Here we recall that we assume all the pictures taken are from a same level. However, this assumption is not always true. If the images have a y-axis drift among all the images, there we have to consider the affine drift removal. Here the affine transformation is given by this equation, and here this is called affine matrix. Basically, affine transformation can preserve the parallel lines, and then we do a simple cropping step that is to remove black stripes appear at the edges of the final results. Now we will evaluate our results.